All right, so you end up recovering the equation for the electric field due to a point charge. All right, so before we move any further, I just want to talk about the dot product just briefly. So what does the dot product represent mathematically? All right, so the dot product represents the following. Imagine that you have one vector pointing in this direction, okay? And then imagine that there's a second vector pointing in a different direction, which is going to be b. If you're looking at the dot product of a and b, this is known as a dot product. So a lot of you guys, it looks like a multiplication. It's not. What this means is you'll be interested in the component of a along the direction of b. That's what it means. All right, so this would be the component of a along the direction of b in essence, which is going to be multiplied by b. All right, so you're looking at the component of a along the direction of b. How much of a is going to be along the direction of b, contributing to the value of b or the multiplication, which means that there would be some kind of an angle in between. The angle is going to be theta in this case. So you're looking at the component of a along the direction of b. So the component of a along the direction of b is going to be cosine of it, right? Does that make sense? So you're looking at the contribution of a to b in essence. Okay, how much does a contribute to b? Expressed as a dot product. So it's not a times b, it's a fraction of a along the direction of b contributing to whatever b is doing. All right. So this is known as the dot product. This is something that you will study in Calc 3 if you've studied it. Obviously, I'm giving you an oversimplified interpretation of it. But this is a big deal in physics. The dot product is something that we'll get to use. All right, so this is your aside. All right, so this is your aside from the topic. How does that work in physics? It works in physics just fine. All right, so imagine that you got your electric field in this direction. So the electric field happens to be pointing in this direction within this region. Except the area, the intercepting area is pointing in a little bit different direction. All right, so I'm just going to come up with some kind of area here. All right, so this is the area that's going to be intercepting the electric field. All right, so the electric field. Notice that the area is not oriented in the same direction. So the area vector is actually oriented in this direction. All right, so there's going to be an angle in between there. This is the angle. So what I'm interested in is the amount of electricity, the component of electricity in the direction of the area vector. That's what it means. Notice that 100% of the electric field is pointing in this direction. I'm only interested in the component of this along this direction. So the component of the electric field along the direction of the area vector is going to be actually small, right? The larger the angle is, the smaller the portion of the electric field pointing in this direction. So that's what the meaning of the flux is. So the flux is going to be represented in terms of the dot product of the electric field pointing in the direction of the area vector. So that's the component of the electric field intercepted by the area is going to give you the flux, which depends on the net charge inside the enclosure and whatever that enclosure is. We're looking at a single surface. All right, so when we actually write this out, it's going to look like this. And then if I were to rewrite this, it's going to look like this. So this is the electric field intercepted by the area of the enclosure, which can be expressed in terms of the angle. Depends on the net charge on the inside. Okay, so this is everything expressed in terms of the vector form using a dot product, and this is the expression in terms of the scalar form. All right, so that's it. Okay, guys, it's 7:32. Take a break for 10. All right, let's go. All right. Earth, is it positive charge, negative charge, or is it neutral? What do you think?
Positive.
Positive.
I don't think so, guys. All these lootings and everything else, it's obviously negatively charged. Earth is negatively charged. It's always been negatively charged. Why is it negatively charged? Well, I have no idea, but it is negatively charged. So Earth is in negative charge, not negative charge. So the next question is, how do we know that? Okay, so how do we know that the Earth is negatively charged? Here's how we know. Here's the Earth. It looks flat because it is dimensionally. The reason why we know that the Earth is negatively charged is because if you can measure the strength of the electric field, it's pointing in the downward direction. Right, so the Earth's electric field points towards the Earth, which means that the Earth is negatively charged. So the question is, what is the value of that charge? So it's 150 newtons per coulomb. directed towards the Earth. So what is the net charge of the Earth? So this is problem number 3 from the handout. It is problem number 3 from the handout. All right, so let's do that problem. While the laptop is still connected. All right, so problem number 3. So the strength of the electric field is what we know. Here's the Earth. And the connection is lost. All right, so it's going to be, what is it, 150 newtons per coulomb? That's it. So the question is, what is the value of the Earth's magnetic electric field in terms of coulomb? All right, how do you do a problem like this? It's what you need to do is you need to use the Gauss law. The best thing to do is just place your Gaussian surface right where the surface of the Earth is. So this is your Gaussian. And look at the net charge inside. And we know that the net charge inside is going to be negative because the electric field always points towards the negative charges. All right, so that's our Gaussian surface. Speaking of that being the Gaussian surface, this thing is spherical. And this is the radius that we're looking at. All right, so our Gaussian surface is spherical. All right, so now we can figure out the net charge right after the Gauss's law. So here's your flux. Here's the strength of the electric field intercepted by this area. Here's the net charge on the inside. All right, guys, here's the electric field. And you notice that the area vector is going to be parallel to it at that point. Okay, so if you express this portion, I don't want my math to be that rigorous, but let's make it rigorous anyway. All right, for the hell of it. For the next level up, the math gets a little bit more sophisticated. Next level up meaning that when you guys take this electricity, electromagnetism, that's where they're going to put the emphasis on math. I don't want to put too much emphasis on math at this point, but ooh, okay, what the hell? Let's just do it. I was kind of uncommitted. All right, so we're looking at this region. All right, so you have E, EA, E, EA, and the cosine of the angle in between. Okay, in the fact that they're pointing in opposite directions, what is the angle in between? What is that angle? This angle that you're looking at is going to be, what is it? 180 degrees, right? So if that's the case, what is cosine of 180 degrees?
-1.
Yeah, that's it. And out of that, strength of the electric field is going to be constant. All right, so here's your area vector. So because of the fact that the angle is going to be 180 degrees, you end up getting a negative. I'll transform my negative to the charge. Oh, I don't like this kind of rigorous mathematics at this level. I want you to be more conceptual and less mathematical, because for the rest of your life, everything's going to be mathematical. You're not going to be able to get to the concepts. All right, math gets so thick that you can't get to physics after a while, or engineering. All right, so this is for a sphere. All right, so what do we know about the sphere? Okay, area of a sphere is going to be 4 pi r squared. Okay, so now let's do a back substitution. So this is going to look like 4 pi r squared times E. You got your negative charge. Solve for the charge itself. All right, so when you solve for the charge itself, this is what you end up getting. All right. This is the final answer. And obviously this is going to be a negative icon, so it's going to be a negative charge. All right, so before we put the numbers in, let's check to see what we got in terms of the numbers. All right, so we got the value of E. Obviously, we have the value for epsilon naught, and we got the value for pi. We know what R is. Okay, guys, R is the radius of the Earth in this case. All right, that's something that you look up Radius of the Earth, I'm guessing that it's going to be 6.38 times 10 to the 6. I think this is the average radius of the Earth. So that's the value that you get to use. And then plug the numbers in. And then when you plug the numbers in, you should get a number. You should get a number, okay. Alright, so just plug the numbers in and tell me what it is. Oh, evidently I have the problem here, so that's fine. Okay, so this is the problem that we were doing. Alright, so this is problem number 7 on a different sheet. Okay, this is a different class. Alright, so here's the strength of the so here's the strength of the electric field. Alright, so it's gonna be negative 6.75 times 10 to the 5th. 675,000 coulombs. This is what we end up getting. That's it. Okay, that's this thing is charging up. Let's move on to something a bit more interesting. So Earth is negative charge. So the question is why? I have no idea. That would be something interesting to investigate. So Earth is negative charge. Airplane is getting struck by lightning.
Fuel bell, lights and AC spot light, fuel bell, disconnect, AC spots over load 1 and 2.
As Apollo disappeared beyond the clouds, Commander Pete Conrad reported catastrophic failures to the electrical systems.
Yeah, the problems here. I don't know what happened. We're not sure we can get by lightning.
Conrad was right. These photographs revealed that it was struck, not once, but twice, by lightning that came seemingly from nowhere. Quick thinking by Mission Control helped them restore power, but it was a close call.
We've had a couple of cardiac arrests down here too, see? I think we need to do a little more all-weather testing. Amen.
It was a problem that needed urgent attention. NASA dispatched test pilots to seek out thunderstorms. Their missions took them through turbulence and hailstones, which could tear a jumbo jet apart.
One of the very early strikes that we had, where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud. As Apollo 12 flew through the cloud of charged ice particles, it left a wake of hot ionized gases and conductive contaminants. The exhaust became a huge streamer, and the burning rocket plasma a giant lightning rod.
Okay, so why is it that stake inside a conductor? A conducting enclosure like the Faraday's. When lightning strikes, it's going to deposit like charges onto the metal surface. In this case, negative charges are being deposited. So the shock is going to transfer negative charges to the metal surface. When you have like charges, what do like charges do? They repel each other, right? They're going to try to get away from each other as far away as possible. What is the furthest that they could get on a metal? It's going to be the surface. So all the like charges will be repelled to the surface immediately. As a result, the net charge is going to remain on the top. So all the net charge itself, excess charge, is going to get repelled to the surface. All right, when the net charge is repelled to the surface, what's the strength of the electric field inside?